Welcome everyone. In this video, we are going to introduce equilibrium calculations and the concept of an ice table to really allow us to quantify how individual concentrations of reactants and products are going to shift from some initial conditions as that system moves towards equilibrium. And so we have four main learning objectives for this mini lecture. We're first going to identify the changes in concentration or pressure that occur for chemical species in an equilibrium system. So you're starting off at some initial values. How are they changing? We then want to be able to calculate equilibrium concentrations or pressures and corresponding equilibrium constants using various algebraic approaches, right? So this is kind of the mechanics of how we go about solving these problems mathematically. And then we want to be able to explain how temperature is going to affect the spontaneity of some processes and relate standard free energy changes to equilibrium constants. Okay, so let's start off with a quick review here. Remember that anytime we are working with a chemical reaction equation, we're going to start doing calculations involving a chemical reaction equation, or really solving any problems. I would recommend you want to make sure that this chemical reaction equation is balanced. And of course, by balance means we have the same number of each atom type on the left and right hand side. So we can see we have two nitrogens on the left, two nitrogens on the right, two of these NH3 gives us six hydrogens here. So we see that in fact we have a balanced chemical reaction equation here for this ammonia decomposition reaction. All right, and so if you're comfortable solving and balancing a chemical reaction equation and you understand our concepts from chemical equilibrium, you've really done all the conceptual work that you need to tackle this entire lecture block. What's left is for us to consider, okay, how do we put these pieces? And so to appreciate that, let's consider a little hypothetical scenario where we suppose that we increase the concentration of N2 by some amount X. And we're just going to always let X be this little positive value, some little positive number. So we're going to start off by just writing this down, saying, okay, my change, remember this delta means change in concentration of N2, which would have units of moles of N2 per liter, is going to increase by some amount X. X is positive, we're going to be increasing it by some plus X. And we want to think, what effect does this have on the concentration of NH3 and H2? So NH3 here and H2 here, how are these concentrations going to be changing? Well, if you consider the stoichiometric ratios here, this is going to guide our understanding. We know that for every X moles of N2 that we've increased the system, the concentration of, then we can convert to moles of H2 using the balanced the balanced chemical reaction equation, looking at the 3 for H2, 1 mole or stoichiometric coefficient of 1 for N2. We're going to plug those in here, and we will see that the constant for every X moles of N2 that you make, you're going to be making 3X moles of H2, right? And again, just 3-to-1 ratio. Similarly, if you are going to be if you're wanting to look at the change in the concentration of ammonia, well, ammonia is going to be decreasing in concentration relative to N2. So if X was some small positive number, we want to use minus X, and it's going to be minus X, and we have to convert between using the stoichiometric coefficients for N2 and NH3 in this 2-to-1 ratio. And you see that, well, for every 1 mole of N2 you form, you're actually going to be losing 2 moles of NH3. Okay, so all of this is just a reasoning going all the way back to your beginning chem lectures where you're working with balanced chemical reaction equations, all right? And so we're just sort of tying these pieces together and saying, okay, what would happen if you change concentrations by a given amount in a given direction, all right? And so what's left for us to do is just one thing is just basically saying, okay, suppose we're given some arbitrary reaction. We want some general method for relating Kc and both initial and equilibrium concentrations of reactants and products. And of course, the way to do this is your Ice table. Okay, not this type of ice table. Basically, what we're going to be looking at is an approach here that allows us to look at the initial change in equilibrium concentrations, hence ice, for given reactants and products, and write those all out in a convenient way that relates them all to that equilibrium constant. And so the idea here is we're going to construct this table a separate column for each reactant and product. So column one here for the reactant one, two for reactant two, three for products. So get it all separated out here, and then a separate row for the initial concentration, change in concentration, and equilibrium concentrations. And so for a generic reaction, A and B coming together to form C, reversible process, we could then write this out and say, okay, whatever those initial concentrations are, which we always denote by a little zero, so times zero, start of the reaction, then some change in concentration is going to occur, for example, minus X, and then we will get an increase of plus X in the concentration of C naught. And of course, once those changes occur, we can add the change to those initial values and we will arrive at our equilibrium concentrations, which could all be plugged into our equilibrium constant expression. Okay, so now I want to take a second and consider some alternative scenarios involving this this ice table here for this simple reaction. Notice that as I have it written here, A and B going to C, it's all stoichiometric coefficients of 1. What would happen if, for example, I introduced the stoichiometric coefficient of 2 here for C? Okay, so if I put a stoichiometric coefficient of 2 for C, I need to propagate that change down through the entire ice table, right? So first of all, I need to make sure that I have a stoichiometric coefficient of 2 here in the top row. And then the change, for every amount X that we use up of A and B, we are actually going to be forming 2X moles of C, or increasing the concentration of C by a factor of 2X. And so at equilibrium, we'd have C naught plus 2X, which means in my equilibrium constant expression, I need to put a C naught plus 2X. And then, of course, also in my equilibrium constant expression, I'd need to put that exponent of 2. And so that same sort of change would have to happen for every one of these terms. You're always going to see let's go ahead and write in another one just so that we've got this down pat. If I were to say put a 4 in front of the A, we'd have to propagate that change all the way down through every number. Okay, but see, I really haven't done anything new. All I've done is saying, hey, you know about chemical equilibrium for a reversible reaction, and you knew how to predict based on the stoichiometric ratios in the balanced chemical reaction equation, how much changes in one will affect changes in the other. And then equation 1 is just basically putting all that knowledge together with our definition for the equilibrium constant. So let's go ahead and see how we can use this concept, the ice table, to solve a problem for us. So in this problem, we're going to be looking at a reaction wherein I2 and iodide react to form I3 minus. This is occurring in an aqueous solution. If a solution with the concentrations of both reactants equal to 1 times 10 to the minus 3 molar, that's our initial concentration, I'll highlight that orange, before the reaction gives an equilibrium concentration of I2 that's 6.61 times 10 to the minus 4 molar, we want to be able to determine what the equilibrium constant for this reaction is. Okay, so at first glance, again, you could pause the video here and give this some thought to see how you go about solving something like this. It seems a bit complicated. However, the ice table is specifically designed to solve just this kind of problem. Because remember what we're doing here. What we're effectively doing is saying, hey, look, we've got some equilibrium constant expression. right? And we know this is going to be a ratio of products over reactants. Things are going to be changing. We're not immediately clear how they're going to be changing, but if we write out our ice table and say, okay, initially we're starting off with this 1 times 10 to the minus 3 molar concentration of both reactants. And again, I didn't say we had any products, so the product's initial concentration is 0. It tells you that if we want to keep X as a positive number, right? And again, that's an option. You wouldn't have to do that. It would just change the sign of everything. But if we want to keep X as a positive number, we can say, okay, well, some amount X is going to be used up of I2. That same amount X is going to be used up of I minus. Again, it's just minus X because the stoichiometric coefficients are 1 in both cases. And for every mole of I2 or I minus that's used up, we'll get 1 mole of I3 minus. So we're going to get some plus X for the change in concentration for I3 minus. And then at equilibrium, we add them together. We say, hey, we've got our initial concentration here. We're going to be taking off some amount, losing some amount X for both I2 and I minus. And then I3 concentration will just be that value X. And so we can plug this back in now to our equilibrium constant expression. Move over a little bit here so you can see it better. And so basically our equilibrium constant, we don't know what that number is, but we know it's going to be X related to X divided by 1.000 times 10 minus 3 minus X, right? And then that quantity is going to be squared because we have that same contribution from I2 and I minus. Okay, so we now have an expression that's telling us what K would be in terms of X. But again, do we have enough information to solve the problem based only on what we have shown here in orange, right? Which is where we've basically only been using the orange highlighted information. Well, of course, the answer is no, not quite. We need to use the information regarding the equilibrium, regarding the chemical equilibrium, where I said, hey, look, at equilibrium, we know how much I2 we have. It's 6.61 times 10 to the minus 4. So this value in purple, highlighted in purple, is actually given to us in the context of the problem. So we can write this down. We can say the I2 concentration at equilibrium. I like to do concentration in the subscript EQ to denote at equilibrium. And that is going to be given by the 6.61 times 10 to the minus 4, which is going to be equal to the 1 times 10 to the minus 3 minus X, which of course allows us to solve for X. Now, once we've solved for X, we can update that ice table, right? Of course, you can plug it directly into the equation if you'd like as well at this point, but we could update that ice table to say, okay, I know exactly how much the concentration is going to be decreasing for reactants, exactly how much it's going to be increasing for products. And so we can carry out the math here and we can plug it in and use equation 1, which is just simply the equation for our equilibrium constant for the reaction to solve for our final value. So let's go ahead and look at another example here. So another example that has slightly different pieces of given information, missing information, however you want to look at it. In this example, we're told that a reaction is being carried out at 2000 degrees Celsius. The value for Kc for the reaction is this 4.1 times 10 to the minus 4. We want to calculate the equilibrium concentration of NO gas in the air at 1 atmosphere of pressure and 2000 degrees Celsius. The equilibrium concentrations of N2 and O2 at this pressure and temperature are given to us here. So what do? Well, we start off by saying, hey, look, I need a balanced chemical reaction equation. So we need to use the given information to say, what product are we forming? And of course, technically, you could write this in either way, but we want to be careful that, how this is worded. inclines us to think that NO is going to be the product. And of course, on an exam, I'll make that nice and clear that, hey, look, these are your reactants, these are your products. I don't necessarily, expect you to be able to fully identify that each time. So I'd probably, on an exam, give you this reaction equation. But of course, you'd want to make sure that you have this thing balanced. So of course, N2 and O2 reactant is going to give you 2 NO molecules. And we were given that reaction equilibrium constant rather. And so when you have this reaction balance and you have the equilibrium constant expression, you can now do some work here. You can say, hey, look, I can write out my Kc. I can solve the Kc for that unknown, the equilibrium concentration of NO in this case, as follows. I just take the N2 and O2, multiply them up to the other side. Then we're going to take a square root to isolate NO by itself. And then we're going to plug in those given values, again, highlighted, color-coded for convenience here, plugging in those equilibrium concentrations. Now, once you have those, you will then figure out that we have equilibrium concentration of NO that is 3.6 times 10 to the minus 4. And remember, the units on this are going to be just molar, as expected. And so as you can see, there are a lot of different ways we can ask these problems. So I think it's helpful to spend a little bit more time and look at a couple more examples involving ice tables and equilibrium calculations. Next one I want to look at involves this reaction here between PCl5 and forming PCl3 and Cl2. So we're told that under certain conditions, the equilibrium constant for this decomposition is 0.0211. And notice here that I'm making it clear that PCl5 is decomposing into PCl3 and Cl2. So it's very clear from the problem what direction to write this reversible reaction for the corresponding equilibrium constant. We are asked to determine what the equilibrium concentrations of PCl5, PCl3, and Cl2 are in a mixture that initially contained only PCl5 at a concentration of 1 molar. Okay, so because only reactant is present, QC is going to be equal to 0, and the reaction will proceed to the right. So we know things are going to be moving towards the right. So we can use this information to help guide the construction of an ice table. Again, most students, and I think conceptually it kind of makes sense to think about X as a little positive number. So if X is a little positive number, we know it's going to be moving to the right. So we're going to be losing some amount X of concentration. Concentration of PCl5 will be going down, and the concentration of products will be going up. Now, again, every term here in the balanced chemical reaction equation has a stoichiometric coefficient of 1. So ones are showing up everywhere here. We got a minus X in the reactants, plus X for both the products, which allows us to write out our equilibrium Now, we have in our third step then equation 1 that allows us to solve for the change in equilibrium concentrations. So to writing this out, we see we have this product over reactants ratio. We know the total answer, but now we're going to plug in terms of X, which gives us an expression Kc 0.0211 equals X squared over 1 minus X. And of course, you hopefully will recognize this as a quadratic. And so one approach, the approach that you could always use for problems like this, is to say, okay, hey, if I've got a quadratic equation, right, or I've got a quadratic equation here, I can use the quadratic equation to solve for X. So quadratic polynomial, you solve for X, you're going to get 2 roots, which are given by the plus and minus. In our good old formula, minus b plus minus b squared minus 4ac all over 2a. And yes, for those of you who don't remember that from grade school, I will give you this on an exam. You don't need to memorize the quadratic equation. Don't you missing points because you forgot a minus sign somewhere. But then what you want to be able to do is take this, plug it into the form, or really what you want to be able to do is take this, plug it into the form that we can read the quadratic equation and come up with those roots. And of course, you're going to come up with two, right? You're going to have an x that's positive and negative here in this case. Now, only concentrations greater than or equal to 0 are physically meaningful. So if we tried to use that x of minus 0.156, this just doesn't make sense, okay? So we're going to be choosing the root to solve this problem that it gives us the positive meaningful concentration values, which lands us with 1 minus 0.135 or a 0.87 molar solution for PCl5, and then PCl3 and Cl2 are both given directly by that value of x. And so once you solve for these equilibrium concentrations, before you move on and say, hey, done with the problem, check your work, okay? All you need to do is plug these numbers back in. Do these given equilibrium concentrations match the equilibrium constant expression? When you plug them back in, they should match Kc. Okay, so some of you might be looking at this quadratic equation and saying, oh, that looks ugly and terrible. Do I always have to do that? Right? So the question comes down, do we always need to use a quadratic equation when solving ice table problems? All right, well, the bad news is that, well, yeah, a lot of times our chemical reaction equations are going to give us higher powers of x than something you can just directly solve. It's like a linear function. So quadratics are very common. However, I want you to think about something, right? If we look at this equilibrium constant expression for this generic reaction here, there's some truths that are present here. If Kc is very large, then that means products are favored, okay? So we're going to have way more products favored at equilibrium. So reactants are converted to products almost entirely, right? So we could make a simplifying assumption and say, hey, well, what if we basically used up all of the limiting reactant to make product if I have a very large K? And then we consider some maybe small change from having used up all of that limiting reactant. Conversely, if Kc is very small, then reactants are going to be strongly favored. And we can say that, well, to a first approximation, we're going to have all reactants, and then we're just going to lose some small amount of reactants. And what we're going to see is that we can use either of these scenarios to make some simplifying assumptions that will allow us to solve these ice table problems very quickly, and oftentimes without needing to do very much algebra. Namely, avoid the quadratic equation. All right, so to see this in action, let's consider a situation where we have a very small Kc. So HCN deprotonating here, we have a Kc value of 10 to the minus 10, so very small. So if you have a 0.15 molar HCN solution, and we say, okay, it's going to start deprotonating, you start off some initial amount of protons and cyanide ions, then some small amount, X is going to be lost of our HCN, and we're going to gain some amount X of our H plus and Cn minus, and then that gives us these equilibrium concentrations. All right. Now, according to equation 1, our equilibrium expression is going to be x squared over 0.15 minus x. Now, we could use the quadratic equation, which I'm not going to make you do here. I'm going to hand you the answer. And it turns out the answer comes out to about 8.6 times 10 to the minus 6. So this is the value that would go in here for both of these x's. And so what I want you to think about is, how does that value of x compare to that initial concentration of HCN, right? I'm measuring my HCN concentration as 0.15 molar. I'm losing 8.6 times 10 to the minus 6. So I'm down there and many decimal points past the significance of the measurement of this HCN. As a result, this minus x term is negligible, and to a first approximation, we can simply ignore it. So if I have 0.15 minus x, if x is much smaller than the initial concentration, then we are going to make the approximation that 0.15 minus x is basically just 0.15. that allows us to rewrite the equilibrium constant expression, where we now just have Kc equals x squared divided by 0.15, right? Because this term, the minus x, is negligibly small. And of course, this allows us for a direct solution by just solving for x, taking the square root, and we arrive at the exact same answer. And the question always comes up, well, am I justified in making this small x approximation? What are the rules there? Okay. Well, we'll talk about some guiding principles more here in a minute. But when in doubt, make the approximation. You can always determine whether or not x was small. You make the approximation, solve x, and if you get a value of x that's on par or influencing values that are significant here for equilibrium constant expression, then that's no good. You can't make that approximation. Unfortunately, you have to go to using the quadratic. And so in our next video, we're going to look at some examples to explore those scenarios where you can use these small x approximations effectively. And your homework will explore these in more detail as well.